Hello, good morning. I welcome all to the virtual version of our Olympia training class. So we shall continue with our present topic, which we started a couple of weeks ago. The topic is the set theory. So far so good. We have been able to discuss some aspect of the set theory, so which involve the definition of set theory. And if you can recall, we define set as an unordered collection of elements. Then it also can be defined as a collection of well-defined objects. Then from there, we talked about ways by which set can be represented. So we said then that set can be represented using two ways, either by the set roster or either by the roster method or by the set builder notation method. When we are applying the roster method, so what that means is all the elements in any given set is going to be listed one after the other. Then the other version of it, which we call the set builder notation method, is a means whereby we talk about elements in any given set by way of description. So in that situation, the membership of such a set or the element that belongs to such a set, is its quality is what is going to be given to us. So once the quality is described, so we now apply what we have learned in previous mathematics class to be able to know what exactly are the number involved or what are the elements involved. Now from there, we also discuss the common sets, and we have so many common sets, but as far as the syllabus that we want to cover is concerned, we are interested only in 4 of those common sets. So the first one there is the set of natural numbers, which we describe by a set of counting numbers, then followed by a set of integers. So and we can see set of integers comprises of both positive numbers and set of what? Of all negative numbers. Then from there, we also discuss the rational number, and we described rational numbers that can be expressed in fraction, or number that can be expressed in ratio, or number that can be expressed as form of numerator and the denominator. For instance, 1/2 is example of what? Of a rational number. How do we list elements of such set? Using the roster method and using the set builder notation method were extensively discussed in previous class. So in order not to waste time, so there will be no need to do or to make much reference about that. Then from there, we also move ahead to discuss elements and cardinality. So by elements, we know those are the items, those numbers contained in any given set. While by the cardinality, we mean the numbers of those elements present in a given set. So if I may talk about that cardinality, so let's make use of set A given above here. So we can see set A comprises of element 1, element 2, element 3, and 4. So now by cardinality of set, so what that means is the number of elements, the number of items contained in this set. And to achieve that, what we are going to do is we count the elements we have in it. So the elements here are 1, 2, 3, and 4. So which shows that what cardinality of set A here is going to be equal to what? To 4. So that is quick revision, or quick let me call it quick revision of what we have done so far. So today we are moving to another useful concept, which we call a subset. And this subset can means a relative term we use to compare one set to the other. So whereby one set we need to compare it to the other set, so we may refer to it as a subset whereby one of the two sets has all its elements present in the other set. So in order to get that better, so we are going to have a very short illustration. So suppose A is a subset of B. So set A, for instance, is a subset of set B, provided every element in A is an element in B. So what this thing is telling us is one set is going to be a subset of the other set once all the elements present in that set can be found in another set to which we are comparing it with. So then the notation for subset is this symbol. So for us to say it to state it mathematically that one set is a subset of the other set is to write it in this form. So the symbol we have here means subset. So then the reading of what we have here now means A is a subset of B. The interpretation to this means all the elements we have in this set A are also going to what? To be found in set B here. And that is just the only thing we have under this subset. Now let's take some few examples. So for example, we have set A being equal to 1, 2, 3. And we have set B equal to 1, 9, 8, 2, and 3. Now the business of the day is to check whether A is a subset of B. So for A to be qualified as subset of B, it shows that all the elements present in A must also be present in B. Now let us check that. I have 1 in set A. Is it present in set B? Yes. I have 2 here. Do I also have it in set B? Yes. I have 3 in set A. Is it also in set B? Yes, it's also in set B. So once all the elements in this set A is also in set B, we can now say that what? Set A is a subset of set B. But mathematically, how do we put that one? We are going to say that this subset symbol, then followed by B, showing that what? All the elements in A can also what? Be found in set B. So that is just what the subset is all about. So let's take another example. If I is equal to 2, 4, 6, 8, and 10, M, that is set M, is equal to 4, 10, set N is equal to 6, 8, and set Q is equal to 2, 4, 8, 6, 10, 12. So we are interested in now determining which is a subset of the other. Now let us compare every other set here to set Q. Now let me start from my set I. Now my set I comprises of 2, 4, 6, 8, and 10. Now since we are comparing I to Q, so we also want to check what are the elements of set Q. So the elements of set Q are 2, 4, 8, 6, 10, and 12. So when we compare the two, we can see that every item we have in set I can also be found in set Q. So as a result, it shows that what? I is a subset of what? I is a subset of Q. So mathematically, that is going to be written as I, this symbol Q, meaning that what? All the elements we have in I are also present in what? In set Q. Now let's also compare set M to set Q here. Now set M comprises of just 2 items, that is 4 and 10. Now let's try and compare that one to set Q. So we can see that 4 and 10 is also present here. So it also shows that what? M is what? Is a subset of Q. So let me say number 2, M is a subset of what? Of Q. Then third one there, which is set N. Is set N a subset of Q? Yes, it is a subset of set Q because the 2 elements we have in N are also present in set Q. So we as well can say that N is a subset of what? Of Q. Or we can say set N is a subset of set Q. So that is that. Then there is this thing that we also have to talk about. That is the concept of proper subset. Now, what we mean by proper subset is there are situations whereby one set we have some elements not present in the other set. So once some of the elements present in one set is not present in the other set to which we are comparing it with, then that is the situation when we make use of proper subset. So, and to introduce the proper subset is more or less the same symbol, only that this sign here that we usually interpret to mean equality is not going to be present. So once we have it in this form, so the reading we give to this one is to say that A is a proper subset of B. And the interpretation of A being a proper subset of B means that there are some elements in set A, which are not present in what? In set B. So to understand that one fully, let's have some example. So I can say that set M is equal to A, B, C, and set T is equal to B, C, D, E, and F. Now, what we want to do now is to check, is A a subset of B? So we can see that, is M a subset of T? Or is set M a subset of set T? So we can see from here that set M is not a subset of set T because there are some elements in set M that is not present in set T. For instance, I have A in set M. A is not present here, but Y, B, and C that are present here are also here. So for a mere fact that A is not present in set T here is enough for us to conclude that what? M is not a subset of T, but M is a proper subset of T because it contains part of the element there, but there is just only one element present in it, which is not here. So to represent this thing mathematically is to say that set M, this symbol, and T, which shows that what? M is a proper subset of T. So remember, when we are interested in talking about proper subsets, so what we interested in is we want to provide just one. It may be more than one, but we need just one element present in one set that is not present in the other set. So if we have such a situation, so we are going to say such a set is what? A proper subset of the other set. Now we can also take another example. Suppose B, set B rather, is equal to 5, 6, 7, 8, and set L is equal to 1, 2, 3, 4, 5, 6, 7. Suppose this is what we have here. So now the next thing is we want to discuss whether B is a subset of L or whether B is a proper subset of L. B will be subset of L if every item we have in set B can also be found in set L. So if not, once only one or more than one element in set B is not present in set L, so we rather call it a proper subset rather than a subset. So we need to get that area very well. So subset talks about situation whereby all the elements in the smaller set are all in the bigger set. When everything we have in the smaller set can also be found in the bigger set, we'll be using the word subset. But if the smaller set comprise or contain an element or more than one element which is not present in the bigger set, now the right word we should use in that situation is going to be what? A proper subset. So to represent this thing mathematically is to say that B, the symbol L. So which shows B is a proper subset of L, and what this means is B contains a particular element, or B contains some elements that cannot be found in what? In set L. So in a nutshell, the symbol we have here means B is a proper subset of set what? Of set L. Now on a final note, suppose we have set Q, set P rather, equals to 1, 2, 3, and set J is equal to 4, 5, 6, 7, 8. Now, the next, what we want to discuss with this question is also to check whether P is a subset of J or whether P is a proper subset of J. So when the two sets here is compared, so we're going to observe that they have nothing in common. For instance, 1 is in set P. Do you have 1 in set J? No. 2 is in set P. It is as well not present in set J. 3 is in set P. It is also not in set J. Then in this situation, we say that P is not subset of J. So once it's not subset of J, it can never be proper subset of what? Of J. So P in this situation is not a subset of set J. Now how do we represent that? So to represent that one mathematically is to say that P subset of J. We initially say P is a subset of J, but we know it is not subset of J. So in order to say that it's not a subset of J, so we just bring a cancellation, just like we did it when we want to say that a particular element does not belong to a given set. So that symbol we introduce then is also what we are going to introduce this time around, which shows that what? P is not a subset of J. And remember, once it is not a subset of J, it can never also be what? A proper subset of J. So remember, the concept of proper subset is borrowed from what? From subsets. So that is the little we are going to talk about today. So in the next meeting or in the next class, we shall move ahead to other aspects of set theory. So